Okay, so thank you, Marina. First, I'd like to thank the organizers. And today, I'm going to talk about this idea of trying to use entanglement as a topological marker in this specific system, which is the confined Hubbard model within the superfluid regime. It's not working. It's still not working. I will have to stay here, probably. Yes. Yes. Well, anyway, here is the outline of the talk. So first, I will give you a brief motivation, how we have been using entanglement to mark quantum phase transitions in more general way. Then I will focus on the Fermi-Hubbard model, the one-dimensional one, and how we are looking at entanglement in these systems, particularly, and then reach the results that will be the main focus here in this talk. So first, every time we think about entanglement or other correlated quantities, and think about concepts from quantum information theory, typically we are used to this type of famous applications. Okay? Should I connect somehow? Just a minute. Oops. No. Yeah, I think it was my fault. I have to allow first here. So now I think it's working. Yes, great, great. Thank you so much. All right. So when we think about the possible applications of these quantum information concepts, in general, we consider these more famous things. All right, okay. And as, for example, quantum cryptography, quantum teleportation, or quantum computing. More recently, you also have these interesting applications where you use quantum information concepts inside a quantum sensors, so in particular for biomedical applications. But today, I want to focus on a different type of application of these concepts, which is related to quantum phase transitions. So how to use tools from quantum information theory applied to condensed matter concepts, right? So I'll be focused here. And now it stopped again. Oh, the internet. All right. Sorry for that. Okay. So to understand better how we can play within these two main areas, I just brought for you a simple parallel between these two areas, right? So when we compare these two, we could imagine that we have we'll stay here in case it doesn't work. But for example, if you compare these two main areas, first thing that we notice is, of course, that they work on different scales. So while in quantum information theory, typically what we have is individual particles, two-level system particles, or with a few particles only. And in contrast, if you analyze systems in condensed matter system, one of the main points is the fact that we have many body typically interacting systems and so on. Now, if you compare the focus on these two different areas, we also see that they focus on different stuff. So from the quantum information point of view, typically one is focused on any information that is encoded in your system, while for the condensed matter point of view, typically we are interested on how to use these informations, these properties in phase and so on. And because their focuses are different, then this means they also explore different properties, different aspects of the systems. And here to cite some, so you could, from this point of view, analyze this, information in terms of storage, processing, and correlations, as the particular one that I will focus today, entanglement one. And while from the condensed matter point of view, in these systems we are interested in states of matter, as for example the superconductivity, superfluidity that I will focus today. But the main idea here is to see that despite the fact that they have different focus and also distinct tools to explore these different aspects, clearly they all are, as almost everything is based on quantum mechanics and have many technological applications. And you can imagine that we have some overlap between the scales within these two communities. So that is just to say that we have a nice playground to work here, because you can imagine that you bring the tools developed from the condensed matter community and analyze the things that quantum information people are interested on, and we can do the opposite way too, right? And well, I've been working on this playground for a while already, since 2017, with some of these works with a couple of collaborators. But then the idea here is, I will focus on the topological aspect, but first, let's imagine what we do have when we are talking about entanglement to quantify these quantum phase transitions, to analyze these quantum phase transitions. So in a very general way, one can define entanglement like that. So if you have just two parts in your system, A and B, and they share entanglement between them, that means you cannot write down the wave function of the total system as a product state of the individual states of the subsystems, right? And that means that, in practical terms, that any measurement in one of the states, the partial states, will be immediately affect the state of the other. Okay, that's quite general and so on, but the point here is that these A and B things can be almost everything. So it could be two particles, yes, it could be spatial regions of your system, of your chain. It could be even different degrees of freedom of a single particle. So A and B is free, of course, depending on how you define this entanglement, we'll get a different result. But one very important thing in this respect is the fact that entanglement is not a quantity that is present or absent only in the system. Instead, we can have different degrees of entanglement in different systems, right? And so that means we could, in principle, quantify the level of entanglement in a given system for a given bipartition or so on. And this will be a very important thing in this respect. So how much entanglement we do have between two parts, A and B, so the degree of entanglement. And also the fact that in general, when you go from one phase to the other, because the structure, the order is very different between these two phases, giving a certain order parameter, you will find difference too in the entanglement structure. So we expect to see this different behavior of entanglement when crossing from one phase to the other, giving a driven parameter. Okay. So, so here just highlighting these two features is because we can quantify the degree of entanglement in a given system and a given A and B bipartition, and because they typically change the behavior, entanglement changes its behavior when crossing this transition, is that we can use then this quantity, this entanglement, as a sound for quantum phase transitions. That is the general idea. Now let's try to be more specific. What kind of entanglement we are talking about and what is our system here in particular in this talk. So we are working with the one-dimensional Hubbard model, which is simply, in the simplest version, is just a single band Hubbard model. So you can have in your chain only single occupied states, or doubly occupied one, or empty. We are just assuming that you have, so we have the hoping term only between first neighbors. Interactions here in the simplest version, that is only on-site interactions that can be attractive or repulsive. I will discuss it in a minute. And in principle, we can adjust, simulate some external potential. Right? Then, if we focus here first in the interaction term, we know already a couple of phases that we can expect from the simplest version of the Hubbard model by just changing signs, for example, in the interaction, and playing with the particle density or the filling factor of the model and the imbalance or polarization within this chain. So we know clearly that for a repulsive interaction, if n is not equal to the half filling, then we have a metallic phase, and we reach the Mott insulator regime when this n equal to 1. Now, for attractive interactions, we can also play with some polarization, some imbalance in this system, and describe, at least qualitatively, for example, conventional superfluidity, just PCS-like. And if we do have an imbalance, a polarization in the system, this could be used to describe exotic superfluidity, this FFLO state, and a normal polarized phase if it's beyond a certain critical polarizations. Well, this is still very general, but now when we plug in the external potential, this Vy term here, we could use, and I will show some results for this type of system. We can use this external potential to simulate random impurity in our system, so a disordered chain. We can also treat, for example, the harmonic confinement case, where we have a parabolic potential, and this will be the main topic of the talk, and clearly many others type, but here another example, we can play with superlattice structure, which is just a modulation in this external potential that repeats periodically. Now, let me just minimize this here. All right. Now, of course, the Hubbard model is quite simple in a sense. I'm assuming the simplest version of the model and so on, t equal to 0. But the main idea here is that it's really some paradigmatic model within the condensed matter community, quantum chemistry, and perhaps material science. And here's just to give you an idea of how paradigmatic this model can be. So if you plug in some extensions in the Hubbard parameters, you can map many very nice models too. Right, and I would say that together with the Heisenberg model, they are essentially cover many aspects and many phenomena from the condensed matter point of view. Okay. Now everything is open. All right. But despite the fact that it's simple, we still have some problems to properly calculate and solve the Hubbard model. For the 1D case particularly, if we consider homogeneous chains, so that's an infinite chain here, we have the exact, whoops, too fast. We have the exact solution for that. That is the Bethe-Ansatz solution, that's fine, but this is for the homogeneous case. We also have some approximate analytical calculations that can be useful, in particular for calculations with DFT, based on local density approximation. And here I'm just citing three of them. One that's not dependent on the spin, so it can be it's very useful, but not for spin-dependent problems. Then there was the next generation of this approach, where we plug in these polarizations, magnetization, so it's also useful to treat systems with magnetization, with some imbalance. And currently we are still making this approach, this parametrization better. We are optimizing it yet. But everything here is for the homogeneous case, right? And by homogeneous, I can already skip then that external potential, the disorder stuff, and the harmonic trap, and so on. So, of course, the realistic system implies some inhomogeneity, some finite size effects, and so on. So, just to cite some, the superlattice structure I mentioned before, the disorder in this particular type, this point-like disorder that I will show some results, and the main topic here, which is this harmonically confined chain. So how we solve the Hubbard model in these situations? Of course, we can do exact diagonalization. My code is only for 20 sites. Of course, with better tools, you can go to larger systems, but I believe not much in this case. So we are in problems with this, with the size of the system. Clearly, we can also use some more powerful tools as these matrix renormalization group calculations. But in this case, we can go with very larger systems, but there is a high computational cost, which is complicated in some case, and I mentioned in particular for the disorder treatment, where we need to, in order to get rid of specific realizations where the impurities lie, I have to perform many realizations of a given set of parameters, and that means 100, 200 samples for a single point. And then if I try to do this with the MRG, I'm simply, well, I cannot really do this, right? In particular, because I cannot also start with a small chain. It has to be big to make sense, this random distribution of particles and so on. So in many cases, the MRG won't be the best choice. Of course, there are several other approximated methods to work with the 1D Hubbard model, but I'm mentioning here one of the approximated ones, which is what we use, that is the dense functional approach, dense functional theory approach. With this, clearly we have an approximation. The quality of this approximation depends on the property you are looking at, and also which kind of functional you have used within the approach. So related to those parametrizations that were in the slide before. But actually for this work, what we will see for the harmonically confined case are only DMRG calculations. So I'm not really at the moment comparing the DFT performance and so on. If you are interested in a comparison between the methods, we have this nice comparison, in particular for quantum phase transitions detection, okay? All right, so now, and how we define entanglement within this chain? So, of course, we could try to map entanglement between particles, and there are nice works analyzing entanglement between two or more particles within the chain. But here, we are sharing our system in parts A and B in a spatial mode, in a spatial approach. That means, for example, I choose one single site, let's call this site A, and ask how much entanglement the occupation states of this site has with the remaining L minus 1 sites, right? So that's what we called ground state single site entanglement, right? So that is really for the ground state, and that's very important because if we have a pure total state in a bipartition, so just two parts entangled to each other, A and B, in this case, we have a well-defined proper for quantify entanglement, which is the von Neumann entropy given here, right? So in this respect, let me just mention that there is in the quantum information community a certain, a typical use of the linear entropy as a same, as a qualitatively, qualitatively equivalent to the von Neumann one. And that is, in most of the case, true, because if you see what is the linear entropy, it essentially measures the purity of these reduced states A, right? So it's in somehow related to entanglement, but is not properly a measure of entanglement. And recently we have found in the Hubbard model regimes where this guy here fails completely to give the trend of the real entropy measure, right? So it's not always like that, but there are regimes where it fails. So for this work, I will focus on the proper measure. And what is this measure after all, right? So the measure, if we Smith decompose the reduced density matrix, we end up with this expression where these W's here are simply the occupation probabilities of that given site. So I've chosen this one in this illustration. That means I will have to calculate the probability of finding the site with a single occupation, either with a spin up or a spin down, doubly occupied, or simply empty site there, right? So these four probabilities are can be written in terms of the filling factor, the magnetization, which is just the imbalance between spin up and spin down, and the derivative of the ground state energy with respect to the interaction. So by knowing this, it's clear that it's a dense functional quantity, and that's why we can use DFT easily with this respect. But the other thing that is interesting to notice is that we can also clearly have obtained this data directly from the DMRG calculation. But one thing that's very important to understand here is that depending on which site I have chosen to be A, that will make a big difference, right? So if I choose, let me see here, if I vary, for example, from one to the other, if I vary these sites where I plug in my reduced density matrix, which is this row A here, and analyze these quantities for that specific site, it may be very different. It only will be independent on the site if it's the homogeneous infinite chain. For any other real application, that depends on the site where I choose. So how we manage that? So first, I will show you some of the results where we are looking at a kind of average entanglement. And that is really the arithmetic average of these quantities. So we calculate how much entanglement I have between a single site, the degrees of freedom in the occupation base of a single site with respect to the remaining sites of that chain. And then I vary this, I do the same calculations for all the sites along the chain, and I take an average. That is the so-called average single site entanglement. And we started to work also in a geometric average in the context of disorder that is called the typical entanglement. So now let's focus on this particular average entanglement. I would like to show you some of the results where we are using entanglement to analyze the quantum phase transitions. Starting with this case, which is the simplest, I would say, which is simply the MOT metal to insulator transition. So we have a repulsive interaction in the Hubbard model. We know that there is the critical point at n equal to 1. And then if you vary this density, this filling factor, in principle, if this property, this average entanglement, can detect something related to the critical point, is there in that place that we will see the features, right? So here we have, for a couple of interactions, we see that if we start with the non-interacting system and vary the filling factor, almost nothing happened for the entanglement, which is the blow curve. So we see the particle hole symmetry, all right? It's maximum there where n equal to 1. That's because for this particular case, there is no interaction. I have my maximally occupation in the system. So it's reasonable to think that with many particles, with the maximum number of particles there, essentially I do have the strongest quantum correlations between the chain, between the sides. And that's pretty much what we see here, the maximum entanglement there, and a pretty boring monotonic behavior elsewhere. Now, if we turn on the interaction, all right, for very small, here, u equal to 1, or for large interactions, then we clearly see that entanglement starts to behave very differently when it approaches to this critical density n equal to 1. So first, we see that this happens only for a certain regime of densities, right? So before this regime here, it was essentially the same for the entanglement, either if it was non-interacting or if you have a very strong interaction, doesn't matter. But as we enter in this regime of particle density, then we really see a non-monotonic behavior related even in just half of the graphic, what means without considering the particle hole symmetry, we see this non-monotonic here behavior. And this is much smaller degree of entanglement when approaching to the critical point. Actually, we find this local minimum at n equal to 1. And this thing here is interesting. Well, this is the signature of the Mott insulator transition seen from the viewpoint of the average entanglement there. But the interesting thing is that it does not go to 0. Instead, the entanglement there reaches a minimum, which is 0.5. We can show it analytically, actually. And the point is that this occurs because in this particular case, the spin degrees of freedom remain in the system, so you still have some finite entanglement there. So we call this just a partially localized state, just to give you a comparison to the Anderson case, which will be shown right now. So now, sorry, why the maximum entanglement doesn't? Yes, it is, but for this, it's a very good question. For this particular case, we have the linear entropy. That's why. Because that's the regime where the linear still works. But you are right. In principle, if I just work with the von Neumann one, it is between 0 and 2. Okay. So now, I was already in the order. Now, what we do is the opposite. We turn off the interaction, and we plug in some disorder here. And we also want to see how entanglement behaves in the presence of a specific type of disorder. And what I'm calling here our disorder is simulated how, right? So that's the point. The idea here is to plug in random a certain number of point-like impurities. All of them in this particular simulation has the same intensity, which is some VI strength. And with that, depending on the number of impurities we choose to plug in there, we have a certain concentration of impurities in the system, right? So that is the particular type of disorder we are simulating here. And if we turn off the interaction, in principle, we are in a Anderson localization regime. And then let's take a look how entanglement signs this localization. So here are the results. It's similar to the previous one in the sense that the driving parameter here is also the filling factor, the particle number of the density of particles. And we also look at the same quantities, the linear entropy and the average one. So I do that calculation with the linear quantity, with the linear entropy, and take an average, a normal average, arithmetic average here, and vary the density for several disorder strengths. So again, if we go to V equal to 0, we have exactly the same graphic that we had before for U equal to 0. So everything is boring, some sense. But now there is something that is different from the Mott insulator signature from the entanglement point of view. Before there was a regime where density makes some sense and change the entanglement, the degree of entanglement in the system. Now, if you look for any small interaction, any small disorder strength that I plug in there in the system, the entire curve simply displays from the no-interacting case. That means there is this change already for very small disorder strength for any particle density. So it decreased, the entanglement decrease for the entire regime. But there are other signatures here that we can see too, in particular for beyond a certain strength of impurity, which is the appearance of this local minima here in particularly, right? And of course here you cannot see clearly, but the position where this minima appears is related to the concentration of the system. So that's why it occurs here, coincidentally, to n equal to 1, because we have 50% of impurities in this particular case, but if I change the concentration of impurities, the position of this minima will also change. But the point is here is that for this particular case, in this particular point, the linear entropy goes to 0 if I increase this V, in contrast to the Mott insulator case. And in the sense that at this particular critical point here, we are seeing a fully localized state. Now, I think I have to hurry a little bit. And well, now I'm going to another case where we have the superfluid scenario. So essentially, I also have the same type of disorder, is the point-like structure, but now I have interactions, but the attractive ones. So U is attractive. And so first, what are the main difference that I see here in that same quantity, this average entanglement? Well, if independently on the concentration of impurities that we plug in there in the system, we see a fast drop of the entanglement degree when increasing the V strength. So here it drops for almost 50% for any concentration of impurities already for a V pretty small, right? And so that is very different from the aspect we saw in the slide before, where there was some minimum strength of the V to see this strong localization, right? Well, and we also see the fast drop and also a fast saturation in the degree of entanglement. That means if I enhance further the degree of the disorder strength, I won't change much the physics there, except in this particular green curve here, which is actually a special place. And if we compare, for example, so here was for several disorders, several concentrations, as a function of the disorder strength. Here we have the opposite. So I have the entanglement as a function of the concentration for several disorder strengths. And we see that there is a particular concentration that makes this interesting and weird features here also seen here. And that gives us also a fully localized state similar to what we saw in the Anderson scenario, with entanglement going to 0 for sufficiently strong interaction strength. And actually this result here we could nicely combine with work extraction in this system in a particular type of quench that we do, we perform in the chain with a smaller chain and so on. But it was nice to see that this particular critical point where entanglement goes to 0 was related to the maximum extraction of work in that particular thing, right? But from this respect, for this third case, I would say that the localization signatures here are both the fast drop and the saturation. And then just to summarize and begin with the real topic of the talk, that was just to give you an idea of how we are using entanglement in this particular type, this average entanglement, to quantify, to analyze, try to mark quantum phase transitions in general. And I could summarize like that. So whenever we see non-monotonicities, maxima, minima, or saturation in the degree of entanglement in a given system with respect to the parameter, the driving parameter, that is typically associated to quantum phase transitions or crossover or localization, right? So now focus on the topological aspects in a confined superfluid chain. This work was performed mainly by Marina, who is somewhere there, and my PhD student, and Isaac Carvalho, who is a postdoc at the moment in our group. And the idea here is that we still play with the 1D Hubbard model. Now, instead of disorder, whatever, we plug in here a parabolic potential. So just to give you an idea of this physics, that's quite simple. So if we have this attractive interaction regime, and you have this confinement, actually for the confinement, you would see the same here. So the particles, due to energy cost of occupying the edges of this chain, we essentially concentrate the particles in the center. But now if we have this attractive regime, that means the particles there are paired. So we have pairs concentrating here at the center, and depending on the strength, the curvature, on the strength of this parabolic potential, you start to see empty sites here. But the point is that then if you change K, which is just the curvature of the potential here, this K, if you change the curvature, the idea is that you start with a superfluid, because U is attractive, but you are concentrate the particles in the center, and at some point, you simply fully occupy all the center sites, and that means you have no mobility at all, and that is a kind of insulator, right? So when the center is fully occupied, we have an insulator. So we could imagine that within this system, by varying K, by varying the confinement strength, we are essentially having a quantum phase transition from a superfluid to a insulator. That's the main idea. So now, how can I address some topological phase in this process, in this quantum phase transition? Sure. That is my, before the last slide, I will mention a little bit about this, if you can wait, I guess. Would be great, otherwise you ask me again. Sure. is one site and the remaining sites, and I take an average. Up to here, I'm considering an average of all these bipartitions. One site and the rest, and then I vary which site specifically I choose. Yes, because of any inhomogeneity you have there. Yes, exactly. Well, those results was for linear entropy, but either linear or von Neumann entropy. Okay, so that's the main idea. So now how can we try to see whether we do have some topological stuff in this process? Of course, clearly in our case, we cannot address some of the typical signatures for topological phase due to the inhomogeneities. So we have to find a way to find signatures in real space. And clearly, there was this idea that, in principle, I could find a way to understand a different or peculiar organization of the electrons in this system in the real space, and I could try to find signatures of this somehow. And for example, just to give you an idea of this, how we can try to see the different organization within the spatial region, one of the possibilities is via what Professor Hesta here called this topological mapping in a local aspect. So really within the sites, see in their case, they really have some Chern number, local Chern number, in the sense that you have 0 or finite number if we have a topological phase there or not. But that was for a 2D, no interacting Rodin model. So despite the fact that we have nice discussions last year in the meeting in Florianopolis, despite that, it was nice and so on, but we could not really map their quantities, their local Chern number to our system, which is 1D, attractive, and with this confinement and so on. So then we also imagine then how can we then have any topological marker in this particular superfluid system, and we decide to focus on this search. Okay, I should see somehow a peculiar behavior of the organization of these electrons if there is any topological stuff in this particular superfluid to insulator transition, right? So our first guess was to look to the density profile, right? So why not to explicitly analyze the density profile? And when we do so, that's what we obtain. So here I have different confinements, so different curvatures for the harmonic trap, and I'm looking at the density along the entire chain. So here are the sites of this chain. And well, first we see clearly that transition that I mentioned before. We start with a superfluid there, homogeneously distributed if there is no confinement at all. But as soon as I turn on the parabolic potential, this accumulates in the center of the trap, and this also brings me to an effective region that is decreasing. That means I started as K is too strong. That means I will have many sites in the borders that are empty because of the potential cost, and I will just essentially decrease this effective chain here in between. All right, so it goes from a superfluid to insulator. But when I look at the density profile, well, we cannot say much about this profile, whether we have some interesting signatures or something that is peculiar, if it's topological or not. We cannot say anything by focus on this respect. One thing that is interesting to mention is that the physics from having a fixed number of particles, and here is n equal to 1, and increase this harmonic trap is exactly the same if we, oh, that was just what we had before, but the physics is exactly the same if we do the opposite, if we fix the confinement and we vary the filling factor. Clearly, it's the same physics, and here's just the numerics confirm that we also see similar stuff, these oscillations and so on, from starting from a superfluid and reaching the fully occupied core centers there, which are calling here a band-like insulator and so on. All right. So now the point is, if I go back to my previous point and try to compare. Oh, sorry, I changed the order of these slides, and I forgot that I have to say this. So we analyze this density profile, and we also analyze some global or average quantities within this chain. To give you an idea what these quantities are, so it's, well, this one we mentioned before is just the average von Neumann entropy. We also analyze in a way that we just consider the trap center. That means we choose here a cutoff for the borders where we will consider a system or not, which defines this effective chain, it is effective size of the chain. And that means we can also look at the entanglement only exclusively in this effective regime. We also bipartite differently the system. Instead of single site entanglement, we bipartite in the half of the chain. That's precisely what is written here. I think I have a figure to illustrate that. So in this case, entanglement here is between half of the chain and the remain in the other half, right? And we also analyze a superconducting order parameter, which is just the pair correlation given by this thing here. Okay. When we look in all these average quantities and so, as a function of one of the parameters, either k, which is the curvature, or the filling factor, we see signatures of the superfluid to insulator transition. And here I'm showing the one with varying the particle filling for a fixed k, which is this number here. Everything here is for very strong attractive interactions, I forgot to mention. And then what we see here are these many parameters, how they see this transition from the superfluid to a insulator one, right? So clearly all of them have some non-monotonic behavior signaling somehow the transition, but there is one of them that is more abrupt, which is the entanglement between the halves, right? So we see that it is much strong, the signature on this particular quantity here, which is this bipartition, gives a much stronger signature. And that is also related to the fact that we are simply disconnecting the two halves at this insulator point, since entanglement between halves goes to zero only there. But now, if I come back to what was my question, whether we could see some unusual distribution of the electronic of the electron in this chain there, we could not really decide. We just have this. But then we thought, oh, perhaps we could look at the entanglement profile as a possible topological marker instead of the density profile. And that's what I will try to convince you, that we do have a topological marker if instead of looking at the average, we analyze the entanglement profile. So what I'm here defining as entanglement profile is pretty simple. So before I choose the site, and then I vary the sites along the chain and take an average. Now I won't take the average anymore. I will just stay with the picture of these profiles of this entanglement. That means when I calculate this, I will have a certain distribution of single site entanglement along the chain. And this is calculated exactly as we did before, right? So I will have a set of entanglement for all single site resolved, so to say, right? And we also do the same for the pair parameter. So essentially, we also analyze the pair correlation also within the single site resolution. And then I have a picture of how entanglement is distributed within that chain. And what we find when we do this approach, then we see very nice and interesting results. So first, we start here. The panels on the top are for a fixed particle density, and I'm increasing. Thank you. And we are increasing the confinement strength, right? So here is just via the confinement strength for fixed particles. On the bottom, I have the same physics, but with the other parameters. So we fix the confinement, and we vary the filling factor, right? And the idea here is that then, when we do that, the black curves are for that entanglement profile. The pink ones are for the pair superconducting order parameter. And what we see is that we start with a superfluid with maximum entanglement or close to the maximum here. And then when we increase the confinement, it starts to appear something here in between that is certain smaller degree of entanglement and a smaller pair correlation here too. And as we go further to the maximum, we see our insulator that we already expected before. So this the core of the trap is fully occupied, has no entanglement at all there. We have just a band-like insulator. But the very interesting thing here is that the degree of entanglement that we started before in a superfluid is kept constant independently on, it appears this thing in between. So we have this thing in the bulk, but the edges of this system stays essentially with the same maximum degree of entanglement and with the same maximum degree of this pair correlation, right? So, and this happens either if you increase confinement or increase the number of particles there, suggesting that this is a robust characteristic of the thing. And well, so from that, we first, I first emphasize the fact that it's essentially constant. It's robust against these two parameters. And also, it's important to notice that we have a very good match between the entanglement and the pair correlation. So it is interesting that we could imagine then the entanglement as a good superconductor order parameter, at least in this system, from these results. But now, when we give a closer look on three of that case, so I have chose one where I just have the superfluid there. So the particle density here is too small. Then if I increase in the intermediate regime, I have something that I will call this a meta. I'll show in a minute why I'm using this name here. And this is insulator. But first, when then we analyze this thing, what we see is that we have an insulator in the core, as the dense profile already suggests, and then any intuitive thought about that particular system would suggest we reach an insulator. But the interesting thing is that we keep the same nature in the same intensity of superfluidity that we have initially here in the entire sample. We kept this thing there in these edges, in these two edges here. So we say we have an insulator in the bulk with surrounded by superfluids there. And if we analyze this thing deep, this intermediate regime here via the charge gap, what we find is that we really have a metallic behavior for this regime here, as already suggested by the degree of entanglement, which was not maximum as in the superfluid, not zero as in the insulator, but some intermediate value here. And also for the pair correlations, it also makes sense that this is a metallic phase in the intermediate regime, but now proved by the charge gap. And with that, we say then we have a robust entanglement at these edges of this insulator. And when we analyze the probabilities of finding particles or empty sites along the chain, we also see that there is a peculiar behavior of the particles in all these superfluid regimes. So while here we see that the two cases, the pairs or the empty probability, which is related to a particle hole symmetry or pair hole symmetry, if you want. So we see that we do have this symmetry here, and this also happens precisely where the entanglement is kept maximum, right? So in the sense that what is protecting entanglement in this case, what is giving this robustness to entanglement is exactly this local pair hole symmetry, local in the sense that it's not in the entire chain that this happens, but precisely there where we saw the maximum edges. So it seems we have a topological structure here with some of the features one would expect from a topological phase, and using the gap, which is also marks well the intermediate phase, that is the metallic case, we depicted this phase diagram as a function of the confinement and the average density for this strong attraction interaction, which is 1 minus 10 in U, right? So that's the main idea so far. And of course now, as you probably have, we also have many questions. First is what we do with this stuff, right? So, and also clearly there are many questions related to that. Either we can, if we can, for example, map this, oh, time is up, so let me run, nice. One of the questions is whether we can map this signature via entanglement stuff with more conventional signatures of topological order. And other questions that is related to Egge's question is, okay, we have this mathematical calculation of this von Neumann linear entropy, whatever, entanglement quantity along the chain, and what this has to do with any possible application of this type of topology we found there, and how we can connect with more other observables and things that we can measure in the lab. And of course, it's not the full answer, but we are also trying to give some insights on this respect, how we could go and connect this mathematical aspects of quantum information theory to something that we can measure. And here is just to give you an example. It's not on that specific system, superfluid systems. Here we have just for the homogeneous 1D system, we could map that average single site entanglement with a quantity that in principle would be easier to measure experimentally, which is the magnetic susceptibility. And we could do this in a universal way, in the sense that we could plug in all of the relation between susceptibility and that entanglement, that mathematical object, in a single line. So in the simplest case. Well, that is also for a superfluid, which means this U is smaller than -2 to avoid the crossover BEC transition or crossover, right? And without imbalance, we also try to map this in the imbalance case, in the FFLO regime. It was not so simple, so universal as in this case, but so then there's a first connection between that object and something that we can measure, but it's for the homogeneous case. And more recently, we also try to do similar stuff in a repulsive system that is with quantum Monte Carlo calculations in collaboration with Teresa Paiva group, where we also found for different geometries, and importantly, for finite temperatures, compared to this case, for finite temperatures regimes, where again these quantities, entanglement and single site entanglement and magnetic susceptibility are related in a very simple way, which is the linear way, right? So in a sense, we would be close to reach real systems or try to talk to experimentalists. Here I would just pass briefly because I'm out of time, but just to do some propaganda of Marina's poster this afternoon, right now, after the talk, where she looked at the FFLO regime, which is this superfluidity scenario, with some imbalance there. She has nice results on there. With that, thank you for your attention. Oh, sorry. Well, you mean between them, right? So yes, we don't have this measure because you are saying perhaps if I can say something of how these sites here are correlated to these others, right? We don't have this measurement, and because here what we are seeing is that in overall, that sites are more correlated to the entire chain than the others, right? So at this regime, I say that the only correlations that remain in the system from a single site resolution point of view are those on that edges. But I cannot, with these quantities, say anything about if the two are correlated. One thing that is interesting to think is for going to the 2D case. While I have in 1D a disconnection between these two, that is one of the properties I showed, the half entanglement between halves. Remember, this would go to 0 at that regime. I think I put here, right? So the fact that this half quantity here, the entanglement between halves, goes to 0 at that regime, says to me that I have disconnected the two pieces. So perhaps this then answer your question. They are not correlated at that point anymore, right, in the insulator regime. They are before, probably, because before would be the metallic phase and somehow. But the point is that if I think of the extension of this work for a 2D scenario, that makes a difference. So one of the questions is, should I see this disconnected between the correlations between the things? Because then I will have a ring, a superfluid ring in a 2D case. So ring, yeah, I think a ring. And then perhaps there they are correlated. Yes, that's a question we also do for ourselves from time to time. Well, what we are using up to now, we are using the following signatures as a topology, in the sense that we have a very specific distribution of particles there. So these are our signatures, right? So it might be not enough. We are trying to find now how to connect with other properties that we could explore. But for us, it's quite a thing that this entanglement becomes robust. It was never seen before on those 1D Hubbard case. Whenever I change the other parameters, in the previous slides I showed to you whether density, disorder, interactions, I always change entanglement there. The same type of entanglement is single site entanglement. We expect to see this quantity varying with the Hubbard parameters. So now, in this particular case, this thing stays there at exactly the same number, at exactly the same level of degree, level of the entanglement. So the same degree of entanglement robust, quite robust, against this density in this scenario, against this, I think I've changed it, against this, all right, okay, here I don't have the parallel. So I have against the density, against the confinement strength, the intensity of entanglement is still there robustly. So that's something that's peculiar in a sense. Also, this particular structure with a insulator and surrounded by this robust edge states. And finally, this metallic intermediate regime. These are our signatures. And might be wrong, of course, but from now, what we have is the thing. So we are saying that we have a topological phase here, but we are not even sure if we have a topological insulator at the bulk or a topological superfluid at the edges. Well, for this case, it seems just 2 points, but if you go to the intermediate regimes, it might be larger, right? It's not 2 points. That depends on the size and the confine. I see. Mm-hmm. Yeah, yeah, I see. Yeah, I see. Yeah, there's no edge states in the sense. Here I'm really saying edges for the geometric distribution of this particle. I'm saying edges, just the edges, but not one thing that's important is not the edges of the confinement. What is also pretty well understood as a phase separation that we could see in the edge. So that's a different thing. But yes, that's one of the points, how we can connect these things with what people are used to see as signatures of topological phase in the real space. Non-local correlations, but non-local correlations in the sense of entanglement. Sorry. Yes, well, that is something that we have. This is non-local. This is really non-local. I know I'm measuring in a site, but it's quantifying the non-locality within all the sites of the chain. So it's non-local correlation. Mm-hmm. That's right. Yes, and saturates logarithmically. Yes. Uh-huh.
Right. So I guess so I'm interested in the fact that your single site entanglement is
Yes.
smaller in the metal than in the superfluid. Right.
Yes, they wanna.
Oh, sorry. So okay. So I think both the superfluid and the metal are described at long wavelengths by a conformal field theory with C equals 1, central charge 1, and the entanglement entropy in the CFT is for an interval is determined entirely by the size of the interval and the central charge.
Mm-hmm.
So I was interested in the fact that your single site entanglement for the metal is always smaller than the superfluid.
Yes.
So I guess it's because the single site is far from the CFT regime. So it's some
I
UV
wouldn't
effects?
say that. Actually, we have old work where we analyze the universal contribution within this conformal field theory for the von Neumann entropy and so on. So via the single site. So it's not far, right? But this may be just a peculiar structure of this particular system. But if we analyze the single site entanglement in homogeneous scenario, we will match exactly the conformal field predictions for the entropy, for the scale of the entropy.
So maybe
by varying the size of the block, right? So you mentioned Cardi and Calabre's work, I suppose. So we do have this match, good, well match between the single site quantity and that theory, that's fine, but not for this particular inhomogeneous case. We never see that.
Because the region that's a metal is only a small interval, maybe.
Oh, okay, maybe, yeah, interesting.
Okay.
Interesting. Thank you.
More questions? No? Okay, we thank again Vivian. And we have another lecture in half an hour, okay?